Hey guys, I'm starting a series of 5 videos on exponential and logarithmic functions, and on this first one, I want to introduce exponential functions and their graph. Hey guys, and welcome back to your channel. If you have not done so yet, go ahead and subscribe so you can get more videos like this one. In this video, we're going to be covering exponential functions and their graphs. So without further ado, an exponential function is a function that can be written in the form f of x equals to b to the power of x, where b here is your base and should be positive and also different from 1. And x is any real number you can think of. Okay, so some examples of exponential functions are going to be f of x equals to 3 to the power of x, also 10 to the power of x plus 2. You could also have negative 2 to the power of x minus 1. Notice here that b, my base, is 2, not negative 2. So this is still positive because the negative is not together with the 2 raised to the power of x minus 1. Another example could be 1 over 2, everything raised to the power of x. In this case, your base is 1/2. And my final example here will be e to the power of x, where e here is the exponential constant. It's a number that goes on forever, like pi. But in my work here, I'm going to be approximating it as 2.72. This last example here is what you call the natural exponential function, and you're going to be seeing it a lot if you're dealing with exponential function, along with the exponential with the base 10. Which happens to be common as well. Here are some functions that are not exponential functions. You could have g of x equals to x to the power of 2. In this case, the base x is a variable instead of being a constant. So this is not an exponential function. And the power here happens to be 2, which is a fixed number instead of any real number that you could put in. And of course, functions like this, we've already talked about them. These are polynomial functions. And in particular, this one happens to be the parabola. Another example will be g of x equals to 1 to the power of x. This is not an exponential function, of course, because b should not be equal to 1. Next, you could have negative 2, everything raised to the power of x plus 1. As you can see here, this is different from the example that we had before, where the negative was not raised to the power of x plus 1. In this case, everything is being raised to the power of x plus 1. So in this case, your base will be negative 2, which happens to be not conforming with our definition of the exponential functions because our base should always be positive. And our last example here that I have that is not an exponential function would be g of x equals to x to the power of x. In this case, you have a variable base, which is not good because your variable should be a constant. Alright, so with that being said, let me go ahead and show you some basics that you should know about exponential functions. So a basic exponential function, as you know already, is going to be f of x equals to b to the power of x, where b is your base and x is your exponent. So in the case of this basic function, your domain is going to be all real number. So it's going to go from negative infinity to positive infinity because every number that you can put in for x would result in another number. There is no number that you can put in that would cause trouble, like you've observed before with root function and rational functions. And in this case, our basic points are going to be the point of coordinate 0, 1, because if you plug in 0 for x into your exponential function, you're going to get b to the power of 0. And you know that every number raised to the power of 0, except of course for 0 itself, is going to be 1. Right? So in this case, 0, 1 is going to be a common point to all basic exponential functions. The second common point is going to be the point of coordinate 1, b, because of course, if you plug in 1 for x, you just get back the base. And so this is going to be also a common point to all exponential functions in their base form. And the last thing I want to mention about exponential function that's very important is the fact that they all have horizontal asymptote. And in their base form, the horizontal asymptote is going to be the x-axis, which is going to be the line with the equation y equals to 0. And so with that, let me show you examples of basic graphs that you could have. So I'm going to go ahead and quickly draft the xy plane here. After that's done, my first example that I want to show you here is going to be the graph with the basic function f of x equals to 3 to the power of x. And so for this basic function, you already know your common points are going to be the point of coordinate 0, 1, which I'm going to put right here, and also the point of coordinate 1, 3, because 3 here is your base, which I'm going to put right here. And of course, you know that this particular function should have its asymptote as the x-axis, so we're going to keep that in mind. So I'm going to go ahead now and connect these 2 points, keeping in mind the general shape of an exponential function and the fact that the x-axis is an asymptote for this particular function. And you're going to get something like this, right? And so this is a common shape for all exponential functions that you should know and keep in mind, as well as you know the shape of a parabola. Okay, so let me give you a second example here in red. It's going to be the function f of x equals to 1/2 all together raised to the power of x. And of course, in this case, my basic points are going to be the point of coordinate 0, 1, which I'm going to put right here, and then the point of coordinate 1, 1/2, which is going to be right here. And of course, keeping in mind that the x-axis here is going to be our asymptote, I can go ahead and connect these 2 points following the general form of an exponential function, and I will be done. And so these are the shape of basic exponential functions. And next, I want to show you how to draft other exponential functions that are not written in their base form. And so my first example here that I want to show you how to draft is going to be the function g of x equals to. I'm going to have 1/2 everything raised to the power of x minus 2, and then minus 1. All right, so to be able to draft this function, I'm going to take the approach that I show you in note 28 and 29, which is to basically draw the basic function first, and then use a set of transformation in order to obtain the draft of my actual function. And so if you need a refresher on how transformations of functions work, you can go ahead and check out note 28 and 29, and that should bring you up to date. All right, so let's go ahead and start here. Of course, my basic function here is going to be the function f of x equals to 1/2 everything to the power of x, because that's the basic exponential function that this new function g is coming from. And my common point here are going to be the point of coordinate 0, 1, and 1, 1/2. All right, so if you look at your f of x function and you look at your g of x function, you should know that the first thing you should do is look at what's being done to the x, the input. And so you can see here that a 2 is being subtracted from the input x. And so keeping in mind that whatever is done to the input should be reflected on the graph in an opposite way, it should be clear here that our first transformation that we're going to do on the graph of f of x is going to be a shift to the right by 2. And then since 1 is being subtracted from the whole function, that will be affecting the output y. And so whatever is done to the output should be reflected exactly on the graph. And so here you're going to have a shift down by 1. All right, so with that being said, I'm going to go ahead and draft my xy plane here again really quickly. And then once I'm done with that, I'm going to go ahead and draft my basic function first. So I'm going to go ahead and put the point of coordinate 0, 1 here. Then I'm going to put the point of coordinate 1, 1/2 here. And then keeping in mind that my graph here should have for horizontal asymptote to the x-axis, I'm going to go ahead and connect these 2 points with that in mind. Now, you really don't have to draft the basic function f of x equals to 1/2 to the power of x here. I'm just doing it here so I can show you what it looks like so you can have a better picture. So you can bypass this whole thing and basically just go ahead and apply the transformation that you have on the basic points and then draft the final draft after that. And so we are going to do that next. And so the point of coordinate 0, 1 is going to be shifted to the right by 2 to become the point of coordinate 2, 1. And then it's going to be shifted down by 1 to become the point of coordinate 2, 0. The same thing is going to happen to the point of coordinate 1, 1/2. It's going to be shifted to the right by 2, becoming the point of coordinate 3, 1/2. Then down by 1 to become the point of coordinate 3, -1/2. And one thing you should keep in mind here that since our asymptote happens to be a horizontal line, any horizontal shift right or left is not going to affect our asymptote, but any vertical shift up or down would in fact affect our asymptote. So in this case, since we have a shift to the right by 2, that's not going to change our asymptote, but the shift down by 1 is going to carry our asymptote from being y equals to 0 to being y equals to -1. And so I'm going to have the new asymptote here at y equals -1. Now, after I'm done with all of that, I know I have my 2 points here and my asymptote. And it looks like if I try to connect those points, I'm going to go ahead and cut the y-axis somewhere. So I'm going to go ahead and do this extra work to find out what my y-intercept is, because that's not too much trouble and it will just give us a better draft. And so on the side here, I'm going to have that my y-intercept is going to be where x equals to 0. And so if you plug in 0 into your function here, you're going to get 1/2 to the power of -2, which happens to be 4, and then -1 would give us 3. And so I'm going to go ahead and put my y-intercept here, the point of coordinate 0, 3, just to give me more direction or more precision as I go ahead and start drafting g of x. And so connecting all these points, keeping in mind the general shape of an exponential function and the fact that y equals to -1 is my horizontal asymptote, I will get the draft of g of x and I will be done. All right, so let me give you one last example to make this whole draft concept sink in. I'm going to have here the function g of x equals to -e to the power of x over 2 plus 2. With that, remember that the negative next to the e here does not make this function not an exponential. It's still an exponential because the negative is not being raised to the power of x over 2, just the e part, which happens to be a positive number. So we are still good here. And so as you can tell here, my basic function is going to be the function f of x equals to e to the power of x, and our basic points here are going to be the point of coordinate 0, 1, and the point of coordinate 1, e. Our e here is of course approximated as 2.72, as we're going to go to the drafting part of this example. All right, so the first thing that's being done to the function here is the division of the input by 2. And so we're going to have to multiply the input by 2 here. And then the whole function is being negated. This will cause the draft to flip over the x-axis because all the positive y becomes negative and all the negative y becomes positive. So that's a flip over the x-axis. And then finally, you have 2 being added to the whole function. So we're going to have a shift up by 2. With that, I'm going to go ahead again and draft my xy plane here really quickly. And once I'm done with that, I'm going to go ahead and first draft my basic function so you can have an idea of what that looks like. So my basic points are going to be here, the point of coordinate 0, 1. And then I'm going to have the point of coordinate 1, e. E here again is going to be 2.72. So between 2.5 and 3. All right, so with that, I'm going to go ahead and connect all those points, keeping in mind that the x-axis is an asymptote for this particular draft. And so next, let me go ahead and apply the transformation on each of those points, including the asymptote. The first point here is the point of coordinate 0, 1. We're going to first multiply the input by 2. Since the input here is 0, that's not going to change the point at all. And then we're going to flip the point over the x-axis to get to the point of coordinate 0, -1. Then a shift up by 2 will bring us back to our original point of coordinate 0, 1. Then let's look at the point of coordinate 1, e. Multiplying the input by 2 will give us the point of coordinate 2, e. Then flipping the point over the x-axis will give us the point of coordinate 2, -e. And finally, a shift up by 2 would land us to the point of coordinate 2, -0.72. With that, let's look at our horizontal asymptote here. Multiplying the input is not going to affect our asymptote. Also, a flip over the x-axis is not going to affect the asymptote either, but a shift up by 2 would move the asymptote up by 2. And so we're going to have that our asymptote becomes the line of equation y equals 2. Finally, all we have to do here is just connect all those points, keeping in mind the general shape of an exponential function and the asymptote. And so what we get here is the draft of the function g of x, and we are done. And so next time I'm going to go through the same process, but I'm going to do that on logarithmic functions, introducing them in the draft. And of course, as usual, if you would like a free PDF copy of this particular note, check out the descriptions below. And don't forget to subscribe to the channel to get more videos like this one the moment they come out. And finally, if you like the way I break down the material, give me a thumbs up and I'll see you next time. Bye-bye.